in this part, we want to talk about the elbow down solution to the two-link planar robot. We just solved how to get the elbow up solution that direction. But in general, in the most part, you're going to have multiple solutions. Three different cases we can have. You can either have two solutions. So you have an elbow up and an elbow down. That's the most common. You could have one solution, and that's basically happens when the combined length is just long enough to get there. So this would be a case where we have to keep them perfectly together to get it all the way to the distance we're trying to get. Zero solutions would happen when L1 plus L2 is less than, is less than L. So I guess by that extension, this would be any time that L1 plus to get two solutions, that's any time L1 plus L2 is greater than just getting an L. So that gives us the option of being able to turn the elbow and get to where we want to be. This can also happen. There might be certain places you just can't reach because of the way it turns. You can turn this anyway, but this can't get back to the point. So, for instance, there's no real way for me to get to a point that's down in here. But usually those are pretty rare. Usually there's something. Usually we can find some way to get to things. And if not, we should have designed a robot differently. We should have made the arms different lengths. Okay, but we want to talk about the elbow down solution. And so we did a lot of work in doing the elbow up solution. The key thing about the elbow down solution is that it's symmetric along the line of action. Of our what was our hypotenuse L. So for the down solution, of course, our theta 1 is going to be this entire angle here, because we have to go rotate all the way to that angle. And then our theta 2 actually rotates from this opposite direction, it turns out. But like I said, what's handy is that these are all symmetric. That this angle in between here and here, that's alpha again, which we solved in the last part. This angle here is gamma again. And so because of that, this angle is the same as negative what theta 2 was for, let's say, for the upper one. So theta 2 for the down equals negative theta 2 for the up. So in this case, it would be negative 63.1 degrees. So that one's easy to solve. And theta 1, you can see, is, well, we could break it down into parts. Remember, this was theta 1 upper. So it's theta 1 upper plus an alpha there plus an alpha there. I'll just write a couple different ways we can get to that. Theta 1 down is equal to theta 1 up plus alpha plus alpha. Of course, another way of looking at that is the theta 1 up plus alpha. We found that angle was beta. So it's also equal to beta plus alpha. And if we go back and get those numbers, remember, actually we have them right up here from just working that last part on getting theta 1 for the upper, that beta was 30.26 degrees and alpha was 25.80 degrees. So in this case, beta is going to be 56.1 degrees if we round it. So that's how we, if we've already solved the downward solution, that's how we could get the, I'm sorry, if we've already got the elbow up solution, this would be how we could get the elbow down solution. Or vice versa. If we'd solved it the other way, we could use those same symmetries and work back this way.